We study conservative force today. Conservative force has a very special nature. It satisfies this simple integral, a vanishing integral, and we have a notation. There's a circle. There's a circle. This circle means this integral is along a closed path. Closed path. It is at least two dimension, but it could be along a one dimension. In one dimensional case, we have integral from a to b plus b to a. That means a to a or b to b. And you know, if it is f of x dx, f of x dx in that case, and we have a primitive function, capital F, whose derivative is a small f of x, then it is f of a subtracted by f of a, and that vanishes in one-dimensional case. When you return to the original, the starting point, this is in two dimensions. The path begins at a certain point and returns to the same point. If this function is this f dot dx is expressed as something, that means this is a total differential of a scalar function. In that case, when you return to the same position, this one becomes a x initial, x final subtracted by x initial, and because it is a closed path, I and final xi is the same as x final, so xi subtracted by a xi, that means it becomes a 0. So the conservative force should always be expressed as a total, when you compute the net work done on the particle along a path that is closed, then the work done on the particle is always 0. Then according to the work kinetic energy theorem, the kinetic energy doesn't change. That means the potential energy is a well-defined function of position. So you will find that the force is always expressed as a gradient. In fact, a gradient is x derivative, x unit vector, y derivative, y unit vector, a z derivative, z unit vector. This is a gradient, and we put the negative sign on it. That is a minus the gradient. If I multiply dx, that is e1 hat dx, e2 hat dy, e3 hat dz. If we multiply this result, f dot dx becomes we have to put negative sign on it, dx, y derivative dy, z derivative dz. We learn that this is a total differential minus du, because u is a function. U is a function of x, y, and z. So the total differential is just sum of partial derivative multiplied by the differential of each variable. Okay? This is the reason why this integral becomes minus du integral, and this one becomes final subtracted by minus, final subtracted by initial position, but because it is a closed path, these 2 points are the same, and eventually this integral becomes 0. Okay, we know the constant force. There should be a potential energy. We are searching for the potential energy that gives force minus mg E3 hat. Let us try gradient x. Gradient x is the derivative with respect to x, y, z, and multiply the unit vectors, right? As you know, y derivative, z derivative vanishes, right? The only non-vanishing contribution is the x derivative only, right? If I take the derivative, this is 1. Therefore, we have a unit vector along the x-axis. In a similar manner, gradient of y survives only for the second component, that is a E2 hat, right? And gradient z, x derivative, y derivative vanishes, only the z component survives, this is trivial 1, and the answer is E3 hat. Therefore, if I make use of these formulas, what I can find is E3 hat equals gradient z. So I can replace this one by mg gradient z. And these are constants. I can move this one inside the gradient. So I have minus gradient mgz. Oh, this should be minus gradient of potential energy. I have indeed obtained the potential energy. That must be mgz. If I substitute this one and repeat the calculation, derivative with respect to x, with respect to y vanishes, only the z component survives, I can reproduce the original result. So this is the now why I can say potential energy of a particle under a constant gravitational force is mgz. Now let us consider this spring force. This restoring force is toward the center, the origin, and we have chosen the x-axis. So let us find the potential energy U that satisfies this conservative force. Because we have found the potential energy in here, this potential energy, by making use of gradient, we have seen that if a force is expressed as a gradient, then this work along a closed path must vanish. Therefore, this mgz is the potential energy that is conservative. Conservative means the total mechanical energy is conserved. Okay. Okay. We remember this one is the derivative of 1/2 kx squared. remember, the integration is not difficult as long as you know how to take the derivative. So you just remember you can obtain this one by taking the derivative of a quadratic function x squared, right? What you need to do is to find out the coefficient. And in this case, it is trivial matching of the coefficient. So what I can say is this is a potential energy. Why? I can take the derivative, my gradient is E1 hat x derivative, E2 hat y derivative, and E3 hat a z derivative, right? And what I have is just x dependence only. The gradient has a non-vanishing component, in this case only. And force is a minus the gradient of potential energy. And in here, I have a force minus kx. The potential energy must be 1/2 kx squared to have this force. Even if we extend this one into 2 dimensions or even 3 dimensions, the shape is always the same. In here, if we consider the 2-dimensional case, what we need to do is just consider 1/2 kx squared plus 1/2 ky squared. In that case, minus the gradient of this potential should be minus kx E1 hat minus ky E2 hat. We know x E1 hat plus y E2 hat can be written as a vector x. So it satisfies k vector x in 2 dimensions as well as in 1 dimension. So even if we extend into 2-dimensional case, we can say the potential energy is of this form. Oh, it is solved in question 4. Sure, if I take the y derivative of this, it does not contribute. X derivative of this does not contribute. Anyway, the same potential energy, 1/2 k x squared y squared. If I take the gradient minus E1 hat x derivative minus E2 hat y derivative of 1/2 k x squared plus y squared, the answer is this. And we can check our calculation by finding the total differential. Minus f dot dx can be computed as, because f equals minus kx E1 hat minus kx E2 hat, so I can write minus f to be like that. And dx is dx E1 hat plus dy E2 hat. That is written in here. And scalar product collects the same component only, so this answer is x dx plus y dy. We know x dx is the total differential of 1/2 x squared. Y dy, we are well trained until now, so I can replace this one with 1/2 kx squared, 1/2 ky squared. And total differentials can be added up, and I have a single total differential of a single function, that is a potential energy. Therefore, this is another way to find out the potential energy of a system. Now we have found the potential energy. This system is conservative. Any integral along a closed path must vanish, and the conservative means the total mechanical energy, and actually that is called Hamiltonian. Total mechanical energy is kinetic energy plus potential energy. Kinetic energy is one half mx dot squared or p squared over 2m. This kinetic energy and potential energy that we just have found, the sum is always conserved. It doesn't change with respect to time. That's the reason why we repeatedly study this kind of calculations. This is another force, and actually you will find that it is in the next semester when we consider a charge distribution along a wire. Then the electric field generated from this wire charge distribution is along the radial direction, and the direction is on a plane. So it depends on the perpendicular distance from a point to the wire. That is the reason why I do not write r. Instead, I use rho, that is a two-dimensional radius vector. This kind of force also appears when we consider a mass distribution along a wire. It is not easy to find the actual application, but in fact that is the same as the electrostatic case we will learn in the next semester. So it is still applicable to the gravitational case. Anyway, in the two-dimensional radial vector as a force, this is also a conservative force. Let us find it if it is true. This is an application of a chain rule. Remember, chain rule. Okay, rho is a square root of something. If I take the derivative with respect to x, let me just take the derivative of this first. That means, let me say a is x squared plus y squared, and I have a square root of a, and I need to take the derivative with respect to x. So I first take the derivative with respect to a first. That is 2 square root of a in the denominator. And then I take the derivative of a. This is a with respect to x. The answer is x over rho. In a similar manner, y derivative and z derivatives are identical to this one, except that I replace this x with y and z. And what happens if I take the derivative of log? Log has a derivative that is a 1 over x style, this one. But I need to take the derivative of rho with respect to x. This is a chain rule. Therefore, I copy this result. Rho's x derivative is x over rho. I substitute this result to find that x over rho squared. Finally, if I combine this result for the y derivative too, I can write it down. This is x component, y component. This is the gradient of log rho. Now, the final result is this is the x vector divided by the perpendicular distance squared rho squared. Now I have found exactly the same structure in it. Haha, and this is a gradient of log. Therefore, I have found the potential energy of this force. This is a conservative force because there exists a potential energy like that. In here, I have divided this row with the dimensional quantity because just like exponential, for example, exponential something that must be dimensionless in physics. So log argument must also be dimensionless. The simplest way to make it dimensionless is just to divide rho by a certain fixed value, rho 0, that has the same dimensions of length. So finally, what I have done is by making use of just the chain rule, I have found what the potential energy of the system is. Another example, this is a very important example. This is for the gravitation and the Coulomb's law of force. And don't be worried too much. Using the same method, I can find the potential energy that represent this conservative force. Okay, key point is a three-dimensional radius, and this radius is a square root of sum of x squared, y squared, and z squared. And I find the partial derivative of this radius with respect to x. Again, using chain rule, I have 2 times the square root of radius, and then I need to take the x derivative of this argument, right? Then this is trivial, it is just 2x, right? So I have 2r in the denominator and 2x in the numerator. So radius, the partial derivative of radius with respect to x is just x over radius. Actually, this is the directional cosine. The directional cosine is I have a radius, and this point has projection onto x, y, and z, and r over x squared, r over y over r squared, and z over r squared. These are cosines along x, y, z axis, and the Pythagoras theorem states that the sum is just unity. Right. A little bit tedious, but a systematic computation can be found for the y and z derivative. And again, I can find the 1 over r's partial derivative with respect to x. This is 1 over r, so I have 1 over r squared. And then, applying the chain rule, I need to take the derivative of r with respect to x. That is just x over r. Therefore, it is x over r cubed. In a similar manner, I just replace x with y and z and sum them over. So gradient of 1 over r is exactly the same as a minus, this is x over r cubed. Oh, I have found exactly the same form. Therefore, this 1 over r is the potential energy of the system that satisfies the Coulomb's law or whatever central force. This is called the central force. Coulomb force or gravitational force is governed by this simple potential that is 1 over r. Fixing the coefficient this negative sign is the same, so the answer is potential energy is K over R. Very simple function. This governs this conservative force. Okay. When the conservative force is applied to a particle, it always has the turning point. The reason is that this total mechanical energy is the sum of kinetic energy and potential energy, and this kinetic energy is always a positive definite. At least it should be zero, but it can never be negative value because it is a real number squared. So with this a positive, or at least it is a zero. The 0 point is called turning point, and positive value, that it means total mechanical energy is greater than the potential energy. The blue curve represents the potential energy, and total mechanical energy is greater than the potential energy. That means that this is the physical range of particle. If it increase the total mechanical energy, we can make this particle to move around the wider region. If I decrease, if it is this red line, this is a total mechanical energy, then there is a turning point, and this outside is the region where kinetic energy becomes negative. That is forbidden. It is impossible, forbidden, and this is allowed. And the extreme values of the allowed region is called turning point because the direction of motion changes at this point. Turn, make a turn, turn to the right, turn to the left, turn, change the direction. That's the reason why we say it is a turning point. However, in quantum mechanics, this region is not strictly forbidden, but it can usually, in quantum mechanics, it describes a tiny particle, the tiny fundamental particle, to behave as a wave. In that case, free particle or the allowed particle in an allowed region is having oscillatory wave function. But in the classically forbidden region, it becomes exponential wave function. So if there is a barrier, classically it turns the direction. This is a barrier. However, electron can penetrate this wall eventually. The left side is this is wavy wave function. It decays the probability, and then it can pass through. It is called tunneling. But we will learn at the end of the next semester when we learn the quantum mechanics. So you should be very familiar with these kind of calculations. This is a planar radius. In radius in 2 dimensions. When we solve the problem of an infinite straight wire and this perpendicular distance from, if we have x, y, z, perpendicular distances doesn't care about the z component. It is just the square root of x squared plus y squared. Anyway, we need to compute the gradient. So we need to find the partial derivatives with respect to x, y, and z. Now you know how to compute this using chain rule. Square root something is 2 times the square root something, and we apply chain rule to find the x derivative of something that is a 2x. So x over rho, y over rho, and because it is independent of z, so z derivative vanishes. So this is now simple. But what happens if I have x over rho squared? Then this is a product of x and 1 over rho squared. So it is multiplied. So I need to take the derivative of first one and derivative of the second one and sum them. So derivative of x appears in here, keeping 1 over r squared intact. And then keep x as it is and take the derivative of this one. That means this, and after that, take the derivative of rho with respect to x. The answer is this is 1 over rho squared, that is rho minus 2, and it becomes a minus 2, and we have a triple power. All right, this one is replaced with the x over rho written in here, and if we combine these two, we have denominator rho squared, 1 over rho squared, and this one is 1 over rho to the fourth power, and we have factor of minus 2x squared. In a similar manner, y over rho squares y derivative is obtained like that. Again, we can find the derivative of y, and you apply the same rule, but this one vanishes. We do not have a contribution of the y partial derivative. Therefore, it is a mixed case, xy different case. We do not have the first term. Instead, this kind of term appears, but we have a crossed one, x and y, instead of x squared. If I combine everything all together, this is the case for the flipped case, xy exchange it. What I have is the same result. Exchanging x and y doesn't change the result. So using this result, everything all together, we can try this kind of problem. This one is slightly different from the previous problem that is radiating in here. Very similar to this, that is a radial. This radial. This is the case when the charge is distributed along a straight wire, then the electric field is radiating along this direction. However, this problem is not radiating. This problem is actually the magnetic field. Magnetic field when the current I is flowing along the z direction. Then magnetic field is rotating about this wire. So this one shows x and y exchange it, and this is a negative sign. You can find that if you multiply this one minus y and x, what is this is a scalar product. This is minus xy plus xy, that is 0. That means this vector minus y e1 hat plus x e2 hat dot x e1 hat plus y e2 hat. This is 0. That means this is perpendicular to each other. Perpendicular to what? The planar radius direction and this direction. So this magnetic field generated by current along a straight wire has this kind of form. Still, we have 1 over r squared style in the denominator. So we will learn that it is It is just Ampere's law. Anyway, by making use of our familiar notation for planar radial vector and tangential vector, using this becomes in a very compact form. By making use of our previous differentiation table, so just to copy these results, substitute to find the curve. This is called the curve. Curve is just like a cross product. First component of a curve is z components y derivative subtracted by y components z derivative. In a similar manner, 2, 3, 1 minus 2, 1, 3. 3, 1, 2 minus 3, 2, 1. Now we substitute all these formulas in here. The final result looks complicated, but at the end of the day, you will find that this curve is 0. So whenever you have x squared plus y squared is not 0, that means you are not along this wire, except for this wire. Everywhere this curve is vanishing. Interesting. We can also compute the curve of this one that we have obtained for, what's that? This one is a spring force, and we know the potential energy is 1/2 k x squared plus y squared, right? Anyway, do not consider the potential energy and just consider the force itself. And the curve is 1, 2, 3 minus 1, 3, 2. And what is f of x? This is a minus kx, and this is a minus ky, and z component is 0. So z component fz is 0, fc, where is fc? This is 0. And what is that? This is minus ky, minus kx, minus ky, minus kx, right? So substitute in here. This should be minus ky, so this should be plus whatever. Anyway, this differentiation becomes 0. This is minus kx, but anyway, xz derivative vanishes. This is minus ky, minus kx, minus k is minus kx of ky minus kx. Anyway, y derivative with respect to x, or x derivative with respect to y. Everything vanishes. This curve is vanishing. Very interestingly, if curve is vanishing, if it is the case, if curve is exactly 0, then there exists a potential energy such that minus gradient potential. This is always satisfied. So computation of a curve looks complicated, but as soon as you compute the curve, and if it is vanishing, it is 0, then you can always find the potential energy. That is a very important point. So potential energy, once you know the potential energy, then you can write it in such a manner. Here, this is a constant, and it does not contribute the force at all, because the force is a minus minus the gradient of potential energy, this derivative kills this constant term. So the reference value at a certain point for the potential energy doesn't contribute to the actual force. This is a simple example of potential barrier. This potential has a bump and there is a well, potential well and potential barrier. Let's see what happens. Potential is increasing, then we know force is a minus the gradient of potential energy. So force is opposite to the direction to make the potential increase. So here potential is increasing. That's the reason why this force is negative. Here it is hidden, it is a zero. Potential is increasing. That's the reason why force is negative. And here, derivative of potential is zero. That means force is zero. Here too, derivative is zero, force is zero. Here, potential is decreasing. That's the reason why force is positive. Decreasing, derivative is negative. I need to put the negative sign on it. So force is positive in this region. In such a manner, we can solve this problem with ease. And this is another similar problem, so you can do it yourself. This is a trivial problem of that indefinite integral. Now, let us look at the curve again. A force has Cartesian coordinates components F1, F2, and F3. And this is how to compute the curve of a vector field. We have a F curve, that is E1 hat 2, 3 minus 3, 2. E2 hat 3, 1 minus 1, 3. E3 hat 3, 1, 2 minus 2, 1. That means epsilon 1, 2, 3. They are positive. That means EI, XJ, FK, and I need to multiply IJK of epsilon. That is summed over I, summed over J, summed over K. That is in here. So always we have 6 permutations, and 6 permutations consist of 3 even permutations and 3 odd permutations. And 3 even permutation says is 1, 2, 3, 2, 3, 1, and 3, 1, 2. And 3 odd permutation is just to exchange any 2 of them. This is 2, 1, 3, 3, 2, 1, and 1, 3, 2. These are positive and these are negative. So we have only 6 contributions, and 3 of them are positive, 3 of them are negative, and these are called even permutations, and these are called odd permutations. In such a calculation, we always use the commutation relation. The derivative of two variables always commute. We can exchange the order, x derivative and y derivative, and y derivative and x derivative, something like that. We can also make use of the anti-symmetry property. That means epsilon ijk. When I exchange the two indices, it becomes a jik, but the exchange will produce the negative sign on it. So ijk, and I can exchange these two, then epsilon ikj. However, I need to put the negative sign on it. So in a similar manner, I can find this ijk, they are the same. So epsilon ijk equals 1/2 times 2 times epsilon ijk, and 2 times epsilon ijk is written in here. And then I can exchange I and j, so j and k, so kj appeared. If I exchange these two, I can find the negative sign on it. This is a trivial example. These are called summed over. So these are called dummy variables. For example, you have the integral f of x of dx. This is always the same as f of y dy. This variable is a dummy variable that does not appear at the end of the day. This answer is independent of y, independent of x. Just like that, these dummy variables can always be replaced with anyone else. All right. Curve of gradient. At the end of the day, you will find that curve of gradient is always vanishing. This is a tedious calculation, but it is due to the fact that if we make use of this kind of relation, gradient, a curve of a gradient of f. All right. What we want to compute is this one. And you will find that these, no, not curve, gradient of a potential energy. What we want to do is compute this kind of form. And we remember it is epsilon I j k e I hat x j derivative, and this is k's derivative of u. Okay, therefore this is sum I, j, and k. You will find this epsilon I, j, k, and we have two derivatives, xj and xk. Second order derivative of potential energy. This one is a symmetric. Under exchange of j and k, and this is anti-symmetric on the exchange of j and k. As a result, the product of symmetric and anti-symmetric structure, when they meet and summed over, this result is always 0. This anti-symmetry is used and this symmetry is used. When they meet together and J and K are summed over, they vanish. It is just like odd function integrated over a symmetric region. It is a 0. They cancel. Now let us train some more about the gradient regarding a radius. Radius in 3 dimensions is just the square root of x squared, y squared, and z squared. We remember the gradient of r is just x over r. In this class we have computed this. And x squared, that is just r squared, and that is r squared is x squared plus y squared plus z squared. So why don't we take the partial derivative of r squared, that is 2x, with respect to y, 2y, with respect to z, this 2z. So x component is 2x, 2x e1, 2y e2, and 2z e3. Aha, that is 2 times x vector, right? If it is an exponential form, I can make use of chain rule. So x squared is 2x. And then why don't we take the derivative of this exponential function with respect to r squared? Then we have over factor 1 over minus 1 over a squared. So even this kind of complicated structure can be computed quite easily. So if I know this, then I can find the potential energy. This potential energy is this. Then by taking the minus gradient of the potential energy, I can compute this conservative force. This is a simple application of the previous problem. Let me show you what happens in this case. We have 1 and 2 contributions. This is a positive contribution and this negative contribution. The positive contribution is at here, and negative contribution is at x equals minus a in here. So there is a potential well and there is a potential barrier. We can draw a contour. This is called contour. The line connecting the points with the same height. This is contour. So these contours are drawn in here. This one represented here, and this wheel is represented by these contours. You will find, because it is potential energy, there is a peak. Potential energy increases, the force is opposite direction. So you will find that the field of force, that is minus the gradient of potential, tends to be radiate from this peak. And then because there is a minimum point, force is toward this direction. This arrows shows that. this conservative force is toward this center, and here diverges from this point to somewhere else around. Okay, understood? This is a potential energy graph, and this is the contour showing the same values along this line. The potential energy is the same, and the force is always perpendicular to this equipotential curve. Okay, equipotential curve, and this force is always perpendicular to the equipotential curve. So let me pass. This is the same problem. Oh, okay. I told you F is expressed in terms of this whenever this one is expressed as a total differential of potential energy. And in addition, if it is called E-rotational, it does not rotate. E-rotational, in that case, always there is a potential energy that describes this force. So from this kind of form, we can determine whether a force is conservative or not. So if it is e-rotation by 100%, the force is conservative, and conservative means the total mechanical energy is always conserved. And force is expressed in terms of potential energy as a minus a gradient of potential energy, then force is conservative. The integral of f dot dx along a closed path is always 0. Every statement is equivalent. And the proof of equivalence of these two statements, curl vanishes, then it is conservative. Any integral along a closed path for the work done by this force is vanishing. That can be proved by making use of Stokes' theorem. And Stokes' theorem is this. This is actually Green's theorem in 2 dimensions. As you know, function a to b dx is expressed as the difference of the primitive function in such a manner, something like that. If we have a curve, this curve something like that, we multiply the scalar product with the area. I mean, 1 dx2 dx3, 2 dx3 dx1, 3 dx1 dx2. If I multiply this and integrate over a surface, it doesn't have to be the closed surface. What we find is x2 f3 x3 f2 multiplied by the first component is this dx2 dx3. and this is 1, 1, 2, 3, 2, 3, 1, 3, 1, 2. So just look at this one only. We have a derivative, single derivative, and we have a double integral. I can always remove this x2 integral in the first term. I can remove the z integral in the second term. So this result will collapse to something like f. If I integrate this x2, what I have is f3 integrated over dx3. But I have integration over x2 will give two contributions at the endpoints. Two contributions. Where is it? Two contributions at the endpoints. And in an area, I have integrated over this. So, for example, I have two x2 and x3. In two-dimensional integral, I have integrated over a single direction. Then what I have is these boundary points. The first part is increasing and the other part has a negative sign. Lower bound has a negative sign. Negative sign means it returns to this. So this double integral, after evaluating a single derivative integral, this one disappears or this one disappears. After that, what we have is just the integral along the boundary. That is the Stokes theorem. Curl surface integral as a scalar product. This surface integral is always shrunken into an integral along a closed path because it is boundary in circle of area. So curl something surface integral is always shrunken into force times the displacement along a closed path. This is the Stokes theorem. So according to this Stokes theorem, if a force is irrotational, that means this curl is vanishing. So integral, you do this integral, this zero integral everywhere. But according to Stokes theorem, this zero is the same as line integral along a closed path. So curl F equals 0 is equivalent to the fact that the force is conservative. That means the work done by this force along a closed path is 0. Who says? Stokes' theorem says. Okay, that's it for today. Any question?